Hi everyone. So today we're going to talk a little bit about an introduction to actually doing a hypothesis test. So we've done simulations, we figured out what they look like, just like we figured out what a confidence interval looked like, and then we went ahead and we made and did our first hypothesis test. This where a bunch of information is going to intersect. So make sure you have your formula sheet handy, your calculator handy, amongst other things. Okay. So we're going to revisit the 80% free throw conversation from the other day. But remember that each class got different results. Both classes got that it's going to fail and that she's probably lying, but each class got a different result. So we're going to start by writing the null hypothesis and the alternative hypothesis. So remember, the null hypothesis is H sub 0, and it is always a parameter, no hats to be worn. Okay, I don't know why that everything is connecting today on my. So P equals, and the claim was that she was an 80% shot. The alternative, which we thought was that she was less than an 80% shot. Okay. And remember, we're going to use the sum of the problem to come up with kind of what our parameter of interest is. So our parameter is the true proportion of free throws made by an 80% shooter. Okay. So again, we know for a fact that every class gets different answers because simulations don't result in the same answers. But usually if they're done well, which is typically with you guys at this point, is we are able to figure out kind of yes or no, right? So we decided that there was evidence to say she was lying, or we're going to talk about the alternative hypothesis. And before we can do that, we want to make sure that we check on a couple of things. So if I can't do a simulation every single time, could I use my knowledge of normal approximations to arrive at the same answer? Yeah, I could. So in order to use a normal approximation, we have a condition that we call normal approximation, or normal. It's the now part of run immediately now. And we said that it deals with the number of successes has to be greater than 10, and the number of failures has to be greater than or equal to 10. Okay. So a lot of students ask, well, Ms. B, is it the number of actual successes and failures or the number of predicted successes and failures? Would I use a P or would I use a P hat? And folks, that's a really good question. If we have a p-value available to us, or a p, a proportion or a mean or something like that for the population, we want to use it. Okay, so in this situation, our little tweak here is that this is 0.8 times my sample size of 50. Is that greater than or equal to 10? And then is my failures 0.2 times 50 greater than or equal to 10? We only substitute for a parameter with a sample when we're doing a confidence interval because we don't have the information that we need in order to know for sure about the population. Okay, and we don't even know if this is valid, but we know that if this was true, would this work? So 80% of 50 is 40, and 20% of 50 is 10. So we can use the normal approximation. Okay. And remember, in our world of conditions, what are the other two conditions that we check? We check random and independent. And again, why do we check random? Right, for bias. Why do we check independent? To see if we can use the standard deviation formulas. Okay. So it states that we know that we're going to use a random sample. Okay. And we know that 50 is less than 10% of all of her free throws. This one is a rough one to necessarily be able to fully absorb that may be true, and that's understandable. We're going to work on that skill. Okay, so now that our conditions have been met, we're going to find the mean and the standard deviation of our sampling distribution. So this is going back to Unit 5. And remember, the things we've seen in the Unit 5 before with the sampling distribution include that as the sample size increases, the standard deviation decreases, and therefore the spread decreases in the data. It has a smaller spread. We also say that as the standard sample size increases, the distribution becomes approximately normal. Okay? So now that we know those conditions, we're going to go back to our notes, and it would be beneficial to pull out your Unit 5 notes and flip them to the back if that would be helpful. I want mu sub p hat, which we say is equal to p. So mu sub p hat, or the mean of p, is going to be equal to 0.8. And the standard deviation of p hat is equal to the square root of p, 1 minus p, over n. So some of you might think to yourself, yo, Miss B, in 2 weeks ago or a week ago, we were making p hats, not p's. Like, why aren't we using hats? Well, you don't want to use a hat unless you don't know information about the population. And for confidence intervals, we don't know information about the population. Okay. But for hypothesis tests, we potentially do. So let's do that calculation. Grab your calculator, do out that calculation for me. I'm slacking, have that calculation. Eight times 0.2 over 50. So I get that this is approximately equal to 0.0566. Okay. So we're going to use this mean and this standard deviation to go back all the way to Unit 1 and label our normal curve the way that we have in the past. So I'm going to add that 0 standard deviation. This would be 0.8. So 1 standard deviation below 0.8 would be 0.7434, and 1 standard deviation above would be 0.8566. Okay, you can go ahead and label all of them if you'd like. So that being said, actually we're going to need to label them, I guess. So this one, I'm only going to go down because that's where we're going to head to. So the number that we're interested in is 0.64. And I had to get all the way to 3 standard deviations to get to 0.63. So now I can come through and I can draw a line about where I think this is, which is about here. Great job, Miss B. Okay. So when you're asked a question like how many standard deviations, that's another way of asking me to find what? Good, a z-score. So remember, a z-score is the value minus the mean over the standard deviation. Okay. And because you know that formula so well and that theory, and you say that over and over again, if I switch it for a hypothesis test, the value becomes the statistic, the mean becomes the parameter, and the standard deviation becomes the standard deviation of the sampling distribution or the standard error. Okay. But what's our value? Our value is 0.64. What's our mean? 0.8 from up here. And what's our standard deviation? 0.0566 from question number 3. Okay, so we can calculate that z-score. And I get negative 2.8269. Okay, which remember, z-squares, we really only have to go to 2 decimal places. But it is critical that we start to understand, folks, that based on what you know about a normal distribution, the probability that I am less than that is very, very tiny. That is a very small percentage. Whether you think about it as an empirical rule with 95, with 68, 95, 99.7, you just think of what you know. That's a very small amount. Okay. So how do we find that probability? Well, we go to table A and we go take a look on our formula. And we find negative 2.8, let's go with 83, so 0, 1, 2, 3. So that is a probability of 0.0023. 0.0023. So the probability that P is less than 0.64 is 0.0023. Is that large or is that small? It's pretty small, right? It's more than pretty small. It's desperately small. So what we're going to do is we're going to say that we're going to use our sentence to make a conclusion, okay? So the p-value is 0.0023, which is less than 0.05, which we're going to use for the standard for this question. Now remember, we do not accept anything in stats. We reject or we fail to reject. So because the p is low, we reject the null hypothesis, or we reject the hoe. So the p-value is 0.0023, which is less than 0.05. The p is low, so we reject, and we're going to state the null hypothesis. We reject the null. Okay. There is significant evidence Mrs. Glass is less than an 80% free throw shooter. Okay, and we'll call it quits there.